that means we're going to see right triangles. That means we're going to see the trig function, sine, cosine, tangent, cosecant, secant, cotangent. We're going to see the unit circle in a couple sections. Next section we'll deal a little bit more with it. What else are we going to see? We're going to talk a lot about angles in degrees and in radians, like you kind of see section 4.1 being about. So it's going to kind of be a review, but it's a review on stuff that we probably don't have mastered, at least not super well. And we need to have mastered a lot better. So let's go ahead and start at the very beginning. At the very beginning of trigonometry, we need to just review angles. So that's going to be kind of our goal for today, is in section 4.1. 4.1 kind of has two parts. One is let's have you get a better idea of an angle, and especially an angle in radian measure. And the second part says, okay, let's introduce you to some physics formulas using those angles in radian measure. So first of all, standard position of an angle. Let's label some stuff. First of all, every angle, thinking back to geometry, every angle has a vertex. A point at which, I'm writing angle, that's the vertex. Every angle has a vertex, a point at which the two sides meet or join or come together. So this isn't like vertex of a parabola, although it's kind of similar. This is the vertex of the angle, and the vertex in standard position, the vertex will always be at the origin. The vertex will be at the origin at 0, 0. Every angle also has an initial side. When in standard position, has an initial side or a starting side. So you have the vertex, which is the point at which the two sides come together. You have the initial side, which is the beginning. So every angle in standard position begins at that spot, and at this spot is what we would define as the positive to the right, the positive x-axis. So the initial side is on the positive x-axis. Now, this is called standard position. There are other ways of doing angles. There's something called a compass bearing that says we don't want to start at the positive x. That would be due east. We want to start due north and actually measure clockwise. So there are other ways of measuring, but this is just standard position. Like when you're in a math class, this is almost always how the angles are being measured. And they have to say if it's not. And there's one more key characteristic of standard positions, but first of all, this isn't a key characteristic, but if that's the initial side, what do you guys think the other side might be called, where it ends? Any ideas? Maybe final. In physics, there's an initial position, final position, initial velocity, final velocity. It's actually not called final, but it's the same idea. It's the ending side, it's the final side, any other synonyms that you might think of?
End.
Ending side, good idea, that's what it means. No? Stopping? Yeah, you're right, that's the idea, it's stopping there. It terminates there? The terminal side. Terminal side. Referred to by terminal velocity. The terminal side. So it initiates on the positive x and it terminates, well, it could terminate anywhere, I suppose. But the third standard position characteristic has to do with the rotation. So let's first of all just talk about a positive rotation. And if positive is one way, well then the negative will be the other way. So a positive angle, which is an angle with a positive rotation, is being measured or is rotating counterclockwise. I don't know if you guys can tell, but these two different angles, one of them is black and one of them is red. Which one do you think is the counterclockwise positive angle? Careful. Which way does the second hand go? It goes around, right? So clockwise would be this. So going this direction, this rotation down to the left, I guess you would say, down to the left. That's actually clockwise. Counterclockwise is the other direction. So this theta, he's going to be, I named it by the Greek letter theta, the lowercase. He's going to be greater than 0, meaning he's going to be a positive angle. But the one on the bottom, the red one that you guys were talking about, since he's rotating the other direction, he's going to be the negative angle. But to be honest, guys, it doesn't have anything to do with actually where it stops. It doesn't have anything to do with the terminal side. This guy has a terminal side too, and it'd be right there. But whether or not the angle is positive or negative has nothing to do with where it ends or where it terminates. It has everything to do with how it rotates. So, for instance, if rotating counterclockwise is all you need to be positive, can you have a positive angle that ends up over here at the red line? Yeah, well, it wouldn't quite be 360 because it wouldn't be all the way around. But couldn't I do 360 minus this angle to figure out how far it needs to go? Yeah, I can rotate counterclockwise all the way around to the red one. So he'd be in this position, but he would have gotten there positively. So any angle that goes counterclockwise or rotates counterclockwise, that's a positive angle. And similarly, can a negative angle get around to this position? Yeah. You just have to do the same thing, 360 minus to get over there. Or just think, go past negative 90, so going this direction, go past negative 180, past negative 270 to get there. And just think, all of the quadrants, if you're thinking about going by 90s, because we know that's a 90-degree angle, you count by 9, so 9, 18, 27, 36. 90, 180, 270, 360. Or the other direction, negative 90, negative 180, negative 270, negative 360. Okay, so that's the interposition. I think that's pretty much all the basics about an angle, like how it gets drawn, initial terminal sides, beginning, endings, and how they rotate. Let's talk about this thing called radians. Let me get back to a single page. Let's talk about this thing called radians. I do want you to draw the pictures. They are kind of important. I'm going to label these guys in this formula so that you guys can see what these variables actually stand for. Some of them you might know, some of them you might not. Remember, one of our goals is to give you a better understanding of what a radian is, what he means, and how he works. First of all, you should probably know radian is just a unit, like feet or inches or miles, like seconds or watts or newtons or ohms. Maybe you don't know that one. Newton meters per second? What's that, joules, I think? Anyway, a radian is just a unit. He's just not the unit we're used to. As for angles, what unit are we used to? Usually degrees. But the sad thing is that degrees actually don't really naturally occur. They're kind of more man-made and contrived in order to have an instrument that has these little tick marks like a protractor where you can get super precise. Radians, it's hard to be precise with, except for just a few. Degrees, it's a lot easier to be precise with. If I were to ask you 14 degrees, you'd get out a protractor, or borrow a protractor, and find me 14 degrees pretty easily and say, oh, it's right here. You'd be pretty stinking close. But if I was to say, give me 1 radian, it'd be a little bit harder to have like a really nice picture of it. Especially if I was to give you something like 0.75 of a radian. You're like, there's no protractor with radians. And there's a reason why. I'll try to explain it in a little bit. But even though degrees, it's really nice for instrumentation, it's really nice for making angles, it's really nice for you guys thinking of what an angle looks like, what quadrant it falls in. Radians. You okay, Jeff? Radians. Naturally occurs. So the struggle is, for some formulas that we're going to see at the end of class, I guess the middle of class tomorrow. For some formulas that we're going to see that have to do with like linear speed and angular speed and some other physics-y type things. And we're not going to get really deep. But you have to have the angle in radians because, well, because of this idea right here. that an angle in radians is equal to the ratio of, S stands for arc length, the distance, that doesn't look like arc, sorry. S stands for arc length, which is just the length of the arc. If you could measure, well, guys, what's the way of measuring something circular? Is there any instrument that we have that can measure like how long a circular object is? I dropped mine. Would a ruler work? You could approximate maybe, right? Like eyeball it, try to bend it and hope you don't break it. It's not so great. Is there anything that's better for measuring circular objects? A compass draws circles. I'm not sure if you can actually measure. They have what?
I don't know, they have a curriculum thing.
Oh, on a protractor, sometimes there's a ruler on the outside. Yeah, that's one way. So the problem is, you have a protractor that has a certain defined arc. What if the circle is like tighter? Or bigger? Like, would that arc be able to follow every single circle, the one on the protractor? No. Draw a line and then... Yeah, you could draw the arc, but how would you know how long it is? Like if I wanted to measure it. What if you've got something flexible? Right? What if you got something flexible and then you tried to follow the arc? Now, you have to have it kind of working with you, which is one right now is not working. But couldn't you kind of follow the arc and then kind of get your fingers to pinch it? Kind of, sort of, maybe. And then like approximate it, because then you can lengthen anything flexible. Even better. Do any of your moms sew? Mm-hmm. Have you guys ever been measured for a suit or for prom or for like a choir dress? If anyone's ever measuring you, they always have a flexible measuring tape, right? Wouldn't that work? If you had a measuring tape, maybe not like one that you would use to build something, those are usually like kind of a little firm, but you could kind of bend them a little bit. But usually like seamstresses or people who are measuring, they usually have some sort of flexible measuring tape, or maybe they use like string like this, and then they take your measurements and then they like lengthen it and then actually mark it with a measuring tape. But as long as you have something flexible, you can actually get this length. The arc length is just how long that actual arc is. Now, do we remember what the arc length is of an entire circle? What's that special name? Not like the measurement, but the name.
Circumference.
Circumference, good. We're going to come back to circumference in just a second. But before we leave the idea of circumference, that's the distance all the way around. It's not just an arc, it's the actual measurement. Well, it is an arc, but it's an arc that's the whole circle. You guys remember a formula for circumference? What does C equal?
2 pi.
You can, careful, that's area.
2 pi.
It's okay, it's easy to get confused. It's either 2 pi r or, does anybody remember the other version? And it's not pi squared, it's area. Pi d. Because 2r is diameter. So you could actually use the circumference or measure the circumference using diameter or radius, right? We'll come back to it in a second. So arc length, distance around. Circumference is the entire distance around. Arc length is the distance around just a portion of it. And that portion is enclosed by an angle. Okay. So arc length and then r, well guys, it's a circle. We know r. R is just, yeah, there you go. R is just the radius. So we have angle in radians is equal to the arc length over the radius. Now that's kind of hard if I just write it and say, oh, of course, you should know what a radian is. Yay, go team. So instead, let me try to help out a little bit. What if I was to say something like, kiddos, how many feet are in 22 inches? What would you be doing? You're doing some good math, and I can see it happening out there. So I take 22 inches. How do we figure out how many feet are in 22 inches?
12 inches.
12 inches. You guys building bridges? 12 inches. Yeah, dimensional analysis. Good. 12 inches is 1 foot, right? So I can say how many feet are in 22 inches. Well, 22 over 12. Does that reduce? Yeah, 11 over 6. Or 1 5/6, right? Now why would we do that? Well, I mean, 22 inches is good, I suppose, but don't most of you have at least generally like the idea of a foot in your head? Like kind of. You're like, okay, so a foot and a little bit more. Well, almost 2 feet. Or you measure yourselves in feet. Like I'm 5 feet tall, I'm 4 feet tall, I'm 6 something. Anyway, long story short. You think about your height in feet too, right? So feet we're a little bit more familiar with than saying that I am 74 inches. You're like, what? I guess I'm 74 inches, I'm 6'2", so then I multiply and then there you go, 74 inches. But who says I'm 74 inches? So when inches start getting really big, we don't think through inches, so then we think feet instead. I want you guys to think of this then. And if I show the ratio 22 over 12, I'm taking a bigger measurement and saying, hey, by dividing by 12, I get to figure out how many feet there are. Okay? That's kind of what's going on with radians. Because in radians, if I was to tell you an arc length, you're like, great, I don't know. So many inches, so many feet, so many miles, depending on how big the circle is. Right? But that wouldn't really tell you exactly like what the actual arc is as far as the angle, as far as how much of the circle it is, unless we divide by radiuses, or the radius, I should say, to figure out how many radii are there in that arc. Let me do a quick illustration. Someone find me a circular object that's pretty uniform around my room. It doesn't matter. Something circular.
Cloth.
The cloth?
Cloth.
The cloth's long. Something a little bit, or too big, a little bit smaller. Paper towels. The pencil sharpener. Okay.
Yeah, paper towel.
I have the pencil sharpener. Paper towels. Actually, I did do that. Maybe we'll do that for the second one. Okay. Ready? Grab my string. I'm going to measure the distance around. So I'm not doing like, it's hard to do part of an arc to be very precise. So I'm just going to go the whole way around, get the entire circumference, so the arc length is the whole thing. So I'm measuring all the way around. Okay, try to get the string to match up. Try to be as precise as possible. Okay. All right, now I'm holding it. Let's see, gets the inches. All right, let's go here to the 0. Okay, what do you think?
It's about 8 inches.
About 8. Let's technically do 7.9. Sound good? Okay, so 7.9 is our circumference of our object. Circumference 7.9, and that was in inches. Now I'm going to measure diameter. Now, I would measure radius, because technically radius is what we need. But radius is really hard to measure. Can anybody think of why diameter would be easier to measure? Yeah, diameter is just all the way across. Radius, you have to go like halfway. That's weird. Okay, so if I go all the way across, I can get there. Looks like this thing is sticking up in the middle. Okay, so the ruler, Gene. That was almost really bad. Okay. I want you guys to get a calculator ready. Yeah, 2.5. We'll say 2.5. You guys divide 7.9 by 2.5. You're taking the ratio of the circumference to the diameter. An arc length 3.16?
2.
I'm kind of impressed with that one. That's better than either of the other ones I did in the other class. Some other, you guys said the paper towel thing? Oh, well, that's kind of, hold on. That's about the same size. Let's do something else like Lysol wipes. Okay. Lysol wipes. I'm going to go around. Circumference, right? Measuring it up. Being flexible will be way more precise than like a ruler. Okay. What do we got? Is it going to fit? Ooh. We'll try. Okay. So it's 12 and 13.3?
Yeah.
13.4. Okay, 13.4. 13.4 is the circumference. You guys got it? You clocked it in? Okay, 13.4. Now let's try diameter. I'm going right through the center. confident about this one. It's kind of rounded on the top, that's kind of hard.
4.1.
Oh, 0.
No.
4.1. Okay, divided by 4.1. What's that one?
3.26.
Ah, okay, that was not as good. 3.26.
Are you trying to make it equal to
What am I trying to make it?
3.4?
Why pi?
Because pi is
What does C over D equal? Pi equals C over D. Wait, so pi is the radian measure of a whole circle? No, that's not right. Do you remember from last year? How many radians are in one whole circle? Not pi. 360 degrees equals what? Oh, we don't remember? 360 degrees? Okay, well, that's all right. I can teach you. Thinking you would come from last year with it. Pi does equal C over D. That's good. But pi is not the radian measure of an entire circle, arc length is the whole thing, because this formula doesn't match. This has D, but what does this have? This has radius. So I shouldn't be using, well, I can use the diameter to get pi, because that is how actually, like in the olden days, pi kind of first came about. They realized the distance around, the distance across, find the ratio. That 3.16 was awesome. Period 2, I had like 3.66 and 3.29. Anyway, a lot better in this class. But, coming back. That's how they first found pi, distance around, distance across, but that's not really where the radians come from. That's just where pi comes from. Radians would come from, instead, doing this one. And saying, hey, what does C over R equal? 2 pi. If I was to divide C by R, I get 2 pi. And 2 pi, I just told you guys on the other page, there's actually a Greek letter for that. And we call that tau. But long story short, okay, so what if I was, now that the formulas match up, what if I was to take my diameters and what if I was to cut them in half? What if I was to take my diameters and cut them in half? So now I'd be doing C over R. What would I get instead? What's 7.9 divided by 1.25? Nope. Hopefully it's 6 point something. What was it? Okay, and did anybody still have the old measurements? That's okay, we'll leave out this one. He was the better approximation anyway. Does anybody know what 6.32 is an approximate for? What's the exact? If I had really precise instrumentation and really even circles without like rounded edges. Okay. What's the 6.32 approximating? What's 2 times pi? 2 times pi. 6.28-ish, right? Okay. So here's the idea. Even though in the olden days pi kind of came about, and even in the Bible it talks about it, back in like ancient times, in India they were figuring this out about the same time that people in China were figuring it out, about the same time people in like, where was the other place? Egypt, I think? Back in like the BCs. The Bible even talked about it when it talked about things with the tabernacle, and I think it was the lever, I think that's where the priests used to wash their hands. But they talked about the ratio that they were supposed to build, like in Leviticus, they had really specific instructions. It had an approximation of pi. But even though pi came from those places, radians don't do C over D, radians do C over R, which means there aren't pi radians in a whole circle. There are 2 pi radians in a whole circle. Now let me show it to you one more way. Sorry, Caitlin's making up her test because she was gone. But she's going to take it during lunch, so she just had to start a little bit. Let me show it to you one more way. Ready? Can you visualize one of those flexible measuring tapes? Like a string, but like with actual units on it. There's usually centimeters and inches measured on it, right? What if I was to wipe that measuring tape clean? A blank measuring tape. It's flexible, I can fold it around. Usually there are units, now there aren't. Okay? And what if on that measuring tape, I was to figure out how big a radius was of a circle, any size circle? Whether it was like the Lysol can, whether it was the paper towels, whether it was the pencil sharpener, any circle, even the clock. Problem is the clock, the circumference wouldn't fit on the ruler, that's why I didn't do that one. But any circle, if I could figure out the radius, and I would go on that measuring tape, and I would go ahead and start at the very beginning, I would mark 1 unit when 1 radius was there. Then I would mark another unit for the second radius. 3 radii, 4 radii. If I was to take that measuring tape after measuring 7 radii, and if I was to fold that measuring tape around the circle, guess where the first unit or the first tick mark would hit? Always at this position. Whatever size circle, whatever the radius is, 1 tick mark on a flexible measuring tape, if I was to fold it around, it would always hit there. The second tick mark would always hit here. The third tick mark would always hit here. The 3.1415926 tick mark, hey, who's that? 3.1415926? Pi. The pi tick mark would hit perfectly halfway. The 4th tick mark would hit there, the 5th, the 6th, and then 6.28, yada, 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 2 pi would hit there. A radian is a ruler, a flexible one, with the radius marked as its units. The radian is the angle where the units would hit on the circle when you fold it around. So why is it called a radian? Just think it's all based on a radius. Why is it called a radian? It's all based on a radius. It's how many radii. How many radii would measure the arcs. And so when I do this ratio, I'm saying, hey, what's the arc length? What's his measure? I divide it by the radius to say how many radii are in there, and that's the angle in radians. Now, why am I telling you this? Well, in homework, if it asks you to sketch or identify the quadrant for 2.5 radians, there's no pi in there. 2.5 radians, what quadrant would you guys have to say that is? Where would 2.5 radians fall? Yeah, in the second quadrant, somewhere between, take your radius, measure him around once, measure him around twice, measure him around 3 times, and back up a bit. 2.5 will be in the second quadrant every time. Maybe it's somewhere around like 150 degrees. Where would 4 radians be? Well, I'd have to hit once, twice, 3 times, 4, yeah, 4 is going to hit in the third quadrant every single time. 5 and 6 are going to hit in the fourth quadrant every single time. Every now and then they ask you to think about radians, and they don't give you pies, and that gets kind of hard. But sometimes they do give you pies, and when they do, it's kind of nice, because a circle is built on pi. Because if I was to go 1 full revolution, like the circumference, 1 full revolution around, I'm going to go 2 pi, 6.28, etc., etc. 2 pi, or 6.28 radii, 1 revolution, would always get me around the circle, all the way around. And once again, that Greek letter I told you that is, same thing as tau. 1 tau, or 2 pi, get me all the way around, it's the same number. I'm going to erase the tau because our book doesn't really talk about it, even though some people online are like, tau would have been so much better. It is what it is. Everything is measured in pi. In the unit circle, and in the precise measurements of angles in the unit circle. So that's 1 revolution. That's going all the way around the circle. That's measuring the entire way. What would half a revolution be, guys? Yeah. So half a revolution would be pi. What would the fourth of a revolution be? Good. Because you cut 2 pi in half, and then you cut pi in half, right? So 1/2 pi. Another way of writing that, so you can make pi over 1 and just say, oh, it's pi over 2. 1/2 pi or pi over 2. 1/2 pi is just pi over 2. Now, if we weren't in the math classroom and I was randomly come up to you and like, hey, you want some pie? What would you think of? Depends on what kind you like, right? Pumpkin, apple, pecan. What else do you get at Thanksgiving?
Banana cream.
Chicken pot pie, there you go. Shepherd pie, are you from Britain? A mincemeat pie?
Oh yeah, coconut cream.
Coconut cream, oh, now we're going.
Banana cream pie.
I'd say fresh strawberry pie, that'd be my favorite. Maybe like a tart? Oh, that's not pie,
Oh,
that's
lemon
circular.
tart.
Some people this morning said cheesecake. I'm sure you would think that's pie, but it's still circular. What if you're in like New York or Chicago and they say like, hey, get me a pie? What are they talking about?
Pizza.
Pieology, they want a pizza pie, right? Okay, here's a dilemma. Do any of those illustrations help us remember that there are two of these pies in a circle? No. You think one pie, one circle, so here's what we gotta think about. Ready? When you think about pie, I need you to think of a calzone. Now, some of you are like, I don't know what a calzone is, so let me enlighten you. Let's do hand raise. Who has never had a calzone? Or even knows what a calzone is? Half the class, this is so sad. Calzone, think of a pizza before it gets cooked, okay? So like nothing is gooey or cheesy or anything. Hopefully you like cheese, otherwise this is so sad. Pizza, right? You fold the dough in half, perfectly in half. Like pinch the edges, probably put extra stuff inside, and then you bake it.
Yeah.
Gooey goodness. Gooey goodness. So my question is, how much of a circle would a calzone be? Oh. Got it. Pie is a calzone. Pie is a calzone. Now for those of you that, it's a hot pocket, but a lot better. And circular, half circular. Anyway, how do you want to describe it? It's like a pizza folded in half with gooey pizza toppings inside. Okay? It's amazingness. Calzone. So I need you to think about pie as a calzone. And that would make sense down here when it says, oh, hey, pie is only halfway. So question, how many calzones will be in the entire thing? Two of them. So I have one calzone up here, one pie. And I have another calzone down here. Okay? That's my two pie. So, I have pi, I'm going to actually move him over here. Pi is the angle measure that measures from 0 to 180. 2 pi is when you come all the way around. But here's the deal. If I cut a calzone, only the top half, right? If I cut a calzone, aka 1 pi, in 6 pieces, okay? Pi over 6, how many 6 do you have?
6.
You cut it into 6, but you only have 1. Now let's say you're being really greedy, but you don't want to take it all. So that means you're going to take all of it but 1. How much do you have? Of your calzone, if you take all of the 6 but 1, you have 5. So where's that going to be? Well, all but 1, isn't that over here? 5 pi over 6? You take 5 of the slices, all but 1. You have 5 pi over 6. What if you take all the slices? 6 over 6, well, now you're back to pi. Okay? What if you take 2 of the 6? How much of that calzone do you have? 2, 6, careful, reduce. 2 over 6 is 1/3. You have pi over 3. Oh, okay. What happens if you take 4 6 or 2/3? Oh, well, you have 2 pi over 3. What happens if you take 3 pi over 3? Well, you have the whole calzone. Now, what if I was to say, now there are 2 calzones, and you want the whole first one and a little bit of the second one. So what if you take 1 and a 6th? Where are you now? If you take 1 whole calzone and another 6th, what would that fraction be? 7 pi over 6. You take all 6 and another 1. What if you want all of both of them, but you'll leave 1 just so you look totally like a pig? Well, how many slices are there if you cut 2 of them into 6? 12, but you left 1. So where are you if you're all the way but 1 short? You only have 11 of those 12 slices. Now hold on, do the same thing with thirds. What if you have the whole first calzone and another third? Where are you at? 4 pi over 3. What if you want all, but you're still going to leave 1? Okay, so what if you have all but 1? Where are you now?
5 pi over 3.
All the angles in the unit circle, guys, are just fractions. You just got to think about pi as a calzone. How many slices is it being cut into, and where am I at? If I have 7 pi over 6, I have a whole 1 and 1 more. If I have 11 pi over 6, I have almost 12 pi, almost 2, but I'm 1 short. Pi over 4, well, you're cutting it into different slices. But if you think about it, if I gave you, if this is pi over 4, if I gave you 3 pi over 4, that's 3/4 of a calzone, where are you?
You're 1 short.
You're 1 short, right over here. What if I give you 7 pi over 4?
You're 3 short.
Careful.
Wait, you're over 3.
Yeah. I have 1 3/4, right? Mixed number. 7/4, 1 3/4. So I have 1, and I have 1, 2. Well, I made my slices 1, 2.
You have 3 more.
Yeah, I have 3 more, which means I'm right here, right? And what did I say that was? 7 pi over 4. Or you can think, how many slices if you have 2 calzones both cut into fourths? That's 8, right? I'm 1 short. Oh. So what would this angle be? If I had all plus 1.
5 times 4?
Exactly, because I have all 4 and I have 1 more, right? The entire unit circle is just fractions as far as the radians go. Yes, we could go ahead and say this is 30 and this is 60 and this is 45. We can count around. We have conversion formulas we'll talk about tomorrow in class, but think in fractions. So if this is 1 pi over 2, where would 3 pi over 2 be?
On this one.
2 over 2 would be here.
So on the number.
3 over 2 is I have 1, 2, and,
Third quadrant.
yeah, I've had 1.5 of the whole thing, which is 1 pi and a half. 1 pi and a half, 3 pi over 2. And then this one is just 1 pi and then 2 pi, and then that one's just 2 pi, and we're done. All of these little angles that you guys saw in the unit circle last year, they're just fractional pieces of pi. So remember, pi is a calzone, half a circle. You need 2 whole pies or 2 whole calzones to make the full circle and go from there. Tomorrow, what are we going to do? We're going to define some special angles like coterminal. And so we still have another 2 minutes, guys. We're going to go ahead and write down this page. Have it ready. We have to define coterminal angles, complementary, supplementary, things from geometry. Not a big deal. Coterminal, complementary, supplementary. Not too crazy. All review from geometry. This page will be a little less review because coterminal, but I'm going to be doing a lot of things with radians because degrees most of you are kind of used to. Doesn't mean we don't need to review where's 220 when you go 180 and 41 in the third quadrant. But radians are the ones you're not as used to. So I will do a lot of things in radians, relating them to things that you did earlier with degrees. But since you guys are writing, coterminal, they share a terminal side. And in order to share a terminal side, if you have one angle that's naturally here, by going, for instance, theta equals 2 pi over 3, we just have to ask ourselves, how do you get there another way besides just turning positively there? And maybe it's going to help for us to think about that this is 120 degrees, and to think in degrees as well. We'll think in degrees, we'll think in radians. But hopefully we'll keep on getting you guys more used to radians so that they're not as scary. But does anybody have an answer for how we could get another angle that also ends here without just making a single rotation? How else could we end there? What could we do? Could we go all the way? That's one way. We could just keep twirling until we get back to it. Or some of you did say we could go the other direction, which also works. But guys, what's going to be the difference between this one and then this one that has this much more? How much got added? 360, 1 full revolution. So we're always going to change by multiples of 360. Or, what is that in radians from today? What's 1 full revolution? 2 calzones? 2 pi, if you want to be snazzy, you can say 1 tau, but that's a whole other variable. Okay, so tomorrow we're going to come back. We're going to work with radians. Tonight, maybe you can start on homework. Maybe. You might not be able to get super far, and that's okay. You might just want to catch up in other classes and then just be ready to do some math over the weekend. That's your choice. I'm just giving you a warning. You might not get super far tonight. We'll start on this page, yeah. We need to actually write in one more formula. All right, so kids, go.
Oh, sorry, I'm sorry.
I got you hopefully just in time for lunch. Bye, guys. Anna, what was it called? The thing that you were comparing to?
Oh, empanada?
Oh, an empanada. I didn't hear what you said. Yeah. Similar. You shouldn't have done it that way. You know that.
我想吃豆腐，好吃。
I figure as long as I can tell, I'll try and give them points.
啊，你严肃，你的
Silly
你的话
kids.
题说的就不正题。